type of statistical analysis that we're going to talk about is something called a chi-square test. X here, this is actually the Greek letter chi. So when they say chi-square, they're referring to this, x with the square. You're never actually going to take the square root of this or anything. You're always going to be solving to get a number for this, and it's called chi-square. What's going to happen is you're going to plug your numbers into this formula, just like the other formulas, and you're going to get a final answer. You're going to compare that final answer to a table that's going to be provided for you, and this is going to allow us to accept or reject a null hypothesis. This will tell us for sure, numerically, whether there is a statistical difference or not between your data sets. Another time you will see the chi-square. This one will come back later in the year because a chi-square test can also be used in genetics. Remember how when you do genetics, you could cross like big B, little b with big B, little b, and then you make a prediction that like 3/4 should have brown eyes and 1/4 should have blue eyes. Like everybody probably remembers Punnett squares. Here's the thing. So let's say that you have 100 people and you get, out of those 100 people, 70 have brown eyes and 30 have blue eyes. Is that close enough to 75%, 25% to say that it matches? How close does it have to be? You know, would 60-40 work? You know, how close? Because you're probably not going to have exactly 75 and 25. That's probably not going to happen. We all know that. So the chi-square test will also tell us in a genetics cross if what we got is close enough to what we expected to accept it versus reject it. So it's going to give us a numerical answer. So really quickly, on the formula sheet, they actually do have this labeled, but what was the sigma? What did that mean? Good. So that means the sum. So we're going to take the sum of, O is going to be observed. They're going to give you that. That's going to be our observed data. And E is going to be our expected data. And that we would have to fill in. So they're going to provide us with the observed. We will have to figure out our expected, which is very easy. I will show you how. And then we're going to plug this in. Now, normally, they will actually provide you with a table for this. So you won't even have to draw this table on your own. So let me show you what the table looks like on the next slide. Yes. So let me show you. So here's an experiment. We have 70 mice, and they are given the option of going towards two different food sources. You have cheese on one side, you have bread on the other side. And below is a table for our data. So you notice the first thing they're going to ask you to do is write a null hypothesis. Let me see if I can move this, make this a little bigger. All right, so the first thing they're going to ask you to do is write a null hypothesis. So a null hypothesis, if you recall, is basically one that says that we don't expect there to be a difference. So our null hypothesis for this would be that there will be no statistical difference between the number of mice, I'm shortening this, I'll just put at each food source to keep it simple. All right, so that's our null hypothesis. Does that make sense? Everybody remembers null hypothesis? And it will always be negative. Null means like zero, no difference. So you will always, always, always write no statistical difference and between whatever your options are. All right, so here's the data they gave you. So this is your observed. And there were 44 mice that went towards the cheese and 26 that went towards the bread. They provided that for you. If you add that together, that's going to give us the total number of mice that they tested, which was 70 mice. All right, now you've got to figure out the expected, how many mice you expected to go to each side. Your total is still 70 mice. Based on a null hypothesis, we assume there's going to be no difference in the number of mice at either side. Therefore, how many mice would we expect to be on either side? 35. To get your expected, you will always basically take your total and divide it by the number of options. Because we're expecting no difference. So we're expecting the same number of mice. If there were 8 options, we would expect the same number of mice at each of those 8 options. This is why the null hypothesis works very nicely for this. We're expecting there to be no difference, so you just take your total, divide it by the number of options, and assume that there will be the same number at each location. So does that make sense? We're good so far. All right, now here's where our formula comes in. So if you recall, our formula was observed minus expected squared over expected. So we're literally going to plug that in and calculate chi-square for each of these. So our first one, observed 44 minus our expected was 35 squared over 35, and we're going to get a number. And then we're going to do the same thing for our second one. Our observed was 26 minus 35 squared over 35. We're going to get a number. And then, since remember how it's the sum, this right here, this box, is where you're going to basically add those two numbers together, or if there were 6 numbers, you'd add all 6 numbers together, and that's going to give us our final number. And then I'll tell you in a second what we're going to do with our final number. So if we plug that into our calculator really quick, 44 minus 35 squared gives us 81 divided by 35, and I get 2.31. For these, I'm going to recommend for a chi-square test, go to the hundredths place. And the reason why is because on the next slide, you're going to see that the table we're going to be using for this always goes to the hundredths place. So go to the hundredths place on your answers. If you work out the second one, 26 minus 35 squared over 35, you actually get the same thing again. That's not always going to be the case. So don't assume if you calculate one that all the other ones are going to be the same. You could get a different answer for each one. You add those together, and our chi-square is 4.62. So this is chi-square. This is our final answer, but now I need to show you what to do with that. All right, so to repeat, here's what we did. We made a null hypothesis, which basically said that we expected there to be no statistical difference. They gave us the observed, and they always provide you, well, at least in the past, with a table that's already set up for you. So all you have to do is put the numbers in the table. They gave you the observed, you add them up, you get your total. To get your expected, you use the same total and divide it by the number of options because you're expecting there to be no difference. So we're expecting the same number of mice at each location. Plug those into our formula, observed minus expected squared over expected. Add everything up, that's what the sum means here. You total it all up, and you're going to get this is your final answer. And this is what we call chi-squared. So chi-squared is 4.62. Yes?
For the bread, you did 81 divided by 26.
For the bread, I did 26 minus 35. It was just observed minus expected squared over expected.
Right. So like the top part would end up being...
Oh, it ended up being 81. Yes.
I got 3.11 for that. I don't know what I did.
Let's see. 26. Did you divide by 35? Make sure you divide it by expected and not by observed.
Oh, I did it by observed.
Yeah, a lot of times people make that mistake. All right, any other questions about this? Okay, so let me show you what to do with that number. So let's remember that number, 4.62. Oops, sorry. And we're going to go, so we filled out our table. All right, our next step, let me rewrite that chi-squared, let me write it over here. So our chi-squared was 4.62, just a reminder. That is the answer that we got. All right, now this is the data table. They are always going to give you this chi-square table. I actually cut and paste this straight from the formula sheet. First thing you'll notice here is that there are 2 rows. You are always going to ignore the second row. I have no idea why they include it. We are always, 100% of the time going to look at the first row, the one that has a p-value of 0.05. So this is the row we're going to be looking at to determine whether we're going to accept or reject our hypothesis. So you can ignore the second row. I don't know why they include it. I assume for some experiments maybe it's useful, but we've never ever used it. In AP we don't use it, and everything I've even ever seen online, they always use this row. So I don't know why they include it. Okay, now the next thing you need to do, you see how this says degrees of freedom, and there's numbers here. You're going to determine which column we need to look at, and it's going to be the number of options from the original experiment minus 1. So if you remember our original experiment, there were 2 options. There was cheese and bread. Those were the 2 options. So our degrees of freedom for this experiment is going to be 2 minus 1, which is equal to 1. Again, it's the number of options. In this case, it was cheese and bread were the 2 options minus 1. And that tells us that that is the column we're going to look at. I'm sorry, wrong column. That here is the column we're going to look at. So in column 1, with 1 degree of freedom, you will see a number here, 3.84. If there were 2 degrees of freedom, we would look at this second column, and the number we would be looking at is 5.99. All right, now here's the key to the whole entire thing. So you're going to look at the 0.05 row, find what we call the critical value is. That is this. This is the critical value. Our critical value for this experiment is 3.84. 3.84 will be our cutoff number. In other words, this is our very last step. If the number we got is bigger than 3.84, then we would reject our null hypothesis. There is a statistical difference here. So we will reject our null hypothesis because our number is bigger than 3.84. If the number you get is smaller than the critical value, then we accept the null hypothesis. There is no statistical difference. All right, and I'll repeat that one more time. So we get our degrees of freedom. That tells us which column to look at. We're always looking at this row. In this experiment, our degrees of freedom was going to be 1. That tells us our critical value, or our cutoff number, is 3.84. If our chi-square that we calculated is bigger than 3.84, which ours was 4.62, it's bigger, that means that the chi-square test fails. And that means we reject our null hypothesis. The difference is enough to say there is a statistical difference between the 2 groups. If we had gotten a number smaller than 3.84, the chi-square test would pass, and we would accept the null hypothesis that there is no statistical difference between the 2 groups. So we're going to do a practice one from the worksheet. We still have 10 minutes, so we should have plenty of time to do that. Oh, okay. So the 2 minus 1, if I go back for a second. Sorry if you were trying to copy that work. Let me go back to this slide. So remember here, there were 2 options. There was cheese and bread. So to get your degrees of freedom, it's the number of original options minus 1. So we had 2 options. Always subtract 1 from your number of options, and we have 1 degree of freedom. If we had put, let's say, cheese, bread, and also carrots, so there were 3 options, then our degrees of freedom would be 3 minus 1, or 2. So it's the number of choices minus 1. Yes? It's probably what I have here, that this will always be the number of options minus 1, probably. Yeah. All right, let me stop this if it didn't already stop.